inshallah, we will discuss part 2 in the topic of variable speed drives. Last week we discussed the basics of reference frame theory, which is used in controlling electrical drives or variable speed drives. Today, inshallah, we are going to go in detail in the power electronic converters. We discussed last class with this diagram for electrical drive system, and we discussed the components of all of the electrical drive systems. One of the drive system component is the power electronic converter. It's one of the essential parts of the power electronic converter. So today, inshallah, we are going to discuss in detail what are the different types of power electronic converters and how we can control these power electronic converters. So simply, shabab, electronic converter, we can make a small definition for a power electronic converter like that. Is an electronic device that can work at high power, because it's not small power, it's working with high power, okay, in order to convert an input power to a suitable or desired output power. So the concept of power electronic converter, shabab, is to achieve certain desired value of power, whatever the waveform of voltage and current. So this is the concept of power electronic converter. So you know all, we have AC machines, we have DC machines, we have special machines. So for all of these types of machines, shabab, we need to make a power electronic converter. So this power electronic converter will be different in topology, which means the connection or the circuit itself will be different according to the topology we have. What is the required output we need? Is it going to be DC, AC, controlled, uncontrolled, pulses, whatever? For instance, when we discuss DC motor, we need DC supply with certain voltage magnitude. When we discussed AC machines, like induction, we need to have certain voltage and frequency at certain times to control our machines. Also, when we discussed stepper motor, for instance, it needs pulses or volt-like pulses, not like a constant DC supply. So all of this can be done by using the power electronic converter. So the power electronic converter itself will be different circuits, but will have the same purpose, which is achieving certain desired output for our motor. So this is the purpose of the power electronic converter. But what are the types of power electronic converters or classification, shabab? We have this classification. We will fastly discuss this today, inshallah. We have AC to DC converters, which are rectifiers. We have AC to AC converters, which are well known as AC voltage controllers, like AC choppers, like cycle converters, like matrix converters. AC choppers are mostly used in our life. Cycle converters are obsoleted. It's made 1940 like that, and it's not used anymore after the appearing of back-to-back converters. Matrix converter is still under investigation. It's not exist yet in industry. So you will find the AC voltage controller industry only AC choppers. Also, we have DC to AC converters, shabab, which is well known as inverter. DC to AC is called an inverter. So we have many types also of DC to AC converters or inverters. We have voltage source inverters, we have current source inverters. These are well-known two topologies for inverters. It exists a long time ago. However, inverters as a voltage source are mostly used in industry because it has better performance in terms of control compared to other type or current source inverters. So we mostly use voltage source inverters. Recently, at 2004, there was a new topology for power electronic or inverters. It's called Z-source inverter. It's made by combining voltage source inverter with an impedance network, and it collects between the advantages of voltage source and current source inverter. So this one is still new and it's not exist yet in our industry. طبعا we discussed recently, شباب, in order to have a topology in our industry, it will take several decades in order to appear in industry, maybe 2 decades to 3 decades like that. Last, type of converter يا شباب is DC to DC converters. طبعا it's used to يعني regulate the DC by a certain way. We have two different types. We have DC choppers. We have voltage regulators. Voltage regulators like buck converter, like boost converter, like buck boost or chuck. So these are the most well-known choppers. DC choppers are mainly used with electrical drives, okay, and يعني with load that doesn't need any filtering or regulation. However, DC voltage regulators like buck boost, or chuck, these four are used with other applications which needs filtering or storing element LNC in the circuit. Okay, you will find buck and boost converters a lot in renewable energy applications and electric vehicles. So these are the most well-known used in these applications. However, DC choppers can be used with DC motors. Okay, because DC motors do not need any filtering, because the motor itself will act as a filter because of the motor inductance itself. So when we use DC choppers, we prefer to use it with electrical machines, but other applications which have no inductance, no internal inductance, we prefer to use the other switching mode regulators, because it has its own filters that will regulate the output. And so these are the different types, Shabab. Now we have AC to DC, we have AC to AC, we have DC to AC, and DC to DC. For the variable frequency drive, Shabab, the mostly used converter is the voltage source inverter. So this will be the focus of today, inshallah, voltage source inverter. Firstly, I will go through the different circuits, Shabab, of topologies. Firstly, for rectifiers, in order to operate inverter, voltage source inverter, you need constant DC. So from where we can obtain, Shabab, the DC? From rectifiers. So we have rectifiers like uncontrolled rectifiers. It may be single phase, like what we can see here. These are the circuits. And we are not going to discuss it, Shabab, in details. I just will mention the different topologies for you in order to discuss in detail, inshallah, the voltage source inverter. So this is here the single phase topologies. Uncontrolled because we used here diodes. We don't have a controlled element, which means, Shabab, the output volt for these types will be constant value. Constant value, I mean the average value is constant, okay? Right. Also, we have three phase. So we have single phase uncontrolled and the three phase also uncontrolled. Three phase uncontrolled, this circuit, Shabab, is used a lot in our life. Is there any question?
Yes, I have a question, Doctor. Regarding this diode, that means constant power. Do you mean, Doctor, the maximum power?
Constant voltage, not constant power. I said constant volt. The output is constant. Output volt is constant, which means uncontrolled.
Okay.
You got it? For that, we call it as uncontrolled rectifier. So the output volt here, all of time, will be fixed value. And if you have here three-phase AC supply, the output volt as average value will be constant all of time. It will be an uncontrolled one. Okay. This one, Shabab, is very cheap and used a lot in our life, even for variable frequency drives. And we will discuss why we prefer to use it. طبعا we prefer to use it compared to single phase or half wave rectifiers, because the waveform here has small ripples. So just a small capacitor can act as smooth or filter in order to give you constant DC. Constant DC, I mean constant instantaneously. It will not be changed instantaneously. However, if you add capacitor or do not add, all of time the average value of the output will be constant, because this is uncontrolled rectifier. Okay. We have also, Shabab, controlled rectifier. Controlled rectifier, we use thyristors instead of diodes. So for these circuits, Shabab, we have many topologies, as you can see. Okay, we have single phase like this. We have semi-controlled or half controlled. Like we have two thyristors with two diodes like that. We may have three thyristors with three diodes in three phase like that, or six thyristors like that. So all of these topologies have its own applications. Based on the application and requirements, we are going to select our topology. But mostly in the high power, we prefer the use of three-phase full bridge. All of time for high power شباب, we prefer the use of three-phase. So what is the difference now between this three-phase one, okay, this three-phase topology, and the previous one, this one? The only difference شباب, تفضل.
The second one we can control the...
Exactly. Yeah. So the second one here you can control the volt. The first one you cannot. It's fixed back. Okay. The concept of control شباب depends. تفضل.
What we are controlling, why we need to control?
Why you need to control? You have a DC motor and you need to control the speed of DC motor by means of volt. So how you can do that?
So we are controlling the amount of voltage, or
yes,
or what?
The voltage magnitude. You are controlling here the voltage magnitude.
Okay.
Okay. So يعني the application of this controlled rectifier شباب are mainly, for instance, are like for instance the DC drives, DC motors controls. تمام. So how we can control? By using something called firing circuits. These circuits will be connected to the thyristor in order to control the output voltage waveform. How? By means of firing angle. Simply يا شباب, it's just something like cutting part of the waveform. So you know the dotted line here is considered as the sinusoidal one. In order to make it DC, you need to convert this negative into positive. Like that, we converted here negative to positive. Okay? This is number one. Number two, you need to control. In order to control, you can cut part of the waveform. So this means you can only decrease the voltage, not increase. Is it right, شباب? Because if you cut part of the waveform, the average value will be decreased. So you can only decrease the voltage and you cannot increase the voltage over the average, maximum average value you can obtain at alpha equals 0. If we consider alpha equals 0 here, this means you have the maximum possible voltage. Okay, and if you decrease or if you increase the value of alpha, it will decrease the voltage magnitude. Here, for instance, شباب, one of the relations used for controlled rectifier, V maximum multiplied by cosine alpha plus phi. And by controlling alpha, in this case, you are going to decrease the amount of V out. So this is the way how we can control the DC output. طبعا we have half wave rectifiers, which means we can control only the positive half cycle. Negative half cycle will be omitted from the waveform. And we have full wave like that. Again, we are not going to discuss in details the operation for each type or like that. We just discuss the concept, شباب. So now we have controlled rectifiers and uncontrolled rectifiers. Okay. This is the output voltage, شباب, for controlled rectifier. Because we have 3 upper switches and 3 lower switches, so we will have VP, which is the voltage for obtained from the upper switches, and Vn from the lower switches, and by subtracting Vb minus Vn, you will get the voltage output like that. So this will be the output waveform if we have controlled rectifier. If we have uncontrolled rectifier, the volt will be the peaks of the line voltage like that, شباب. Okay. The one we already could see in previous slides. So this is now the output voltage in case of controlled 3-phase rectifier. Okay. Take care. All of the circuits we have discussed here are based on thyristors, not transistors or IGBT or MOSFET. Okay. All of these now are based on thyristor elements. Okay. Second type of converters, which is DC to DC converters. DC to DC converters, we already discussed one of them in controlling DC motors, which is a 4-quadrant DC chopper. It depends on the operation, in something in control called duty cycle, which is the ratio between turn on time over the overall period of the switching time. So this is now called the duty cycle. By controlling duty cycle, you can control the output voltage of a DC converter or DC chopper. We have, by the way, DC chopper, شباب, and we have switched mode regulators. Switched mode regulators act as transformer, which can step up, step down like transformer exactly. You know, you have AC transformer, you don't have DC transformer. So in order to have equivalent to DC transformer, you can use switched mode regulators. Okay. What are the different types of DC to DC converters? Firstly, for the DC chopper, شباب, we have many circuits for DC chopper. We have class A, where in class A we have positive voltage and current. This is the circuit of class A, and this is the output quadrant. Okay. We have also class B, where you have positive volt and negative current like that, which can be used in the regenerative mode for any supply, but just during that mode. Okay. We have also class C or type C. We can call it type C or two quadrant type A. Okay. There are two names, either type C chopper or two quadrant type A, where you have voltage here in positive and current is bidirectional, can go and back and forth. This is widely used if you need bidirectional power flow, because the current will go from the source to load or from load to source. And this is used in battery charging, because in battery you need to charge and discharge. If it is connected to grid, sometimes you will need to charge the battery, and sometimes to stabilize the energy or stabilize the network, you can discharge the battery again. So in order to make a charge and discharge for batteries, you need bidirectional circuit, which can flow the current in positive or negative. So this circuit is used a lot in bidirectional current. Okay. Here also we have another type which has positive current with positive and negative voltage. It's called type D or two quadrant type B. Okay. And finally we have class E or type E, which is four quadrant, and this is the circuit what we have discussed in detail in the four quadrant control of DC motors. For the switched mode regulators, we have four well-known topologies. One is called the buck converter. It's used as step down, and the relation between V out and V input is D. And all of time, D is between 0 and 1, which means this converter will be step down converter. For the other converter, here in figure C, this is called the boost converter. Boost converter relation between V out and V input is V out equal Vm multiplied by 1 over 1 minus D, which means if you apply here a value for D, you will have output voltage higher than the input voltage. However, you have here a limitation to have a gain of 4 maximum. You cannot increase the gain over 4. If you substitute here with the value of D, you can find that, for instance, we said D can vary from 0 to 1. What will be the value if we make D equals 1? What will be the output voltage in this case?
Infinity.
It will be infinity. So theoretically, it's infinity. Practically, you cannot reach to that value, because the circuit will be burned before reaching to that value. So the maximum possible gain is 4, which means if you substitute here 1 over 1 D, 1 over 1 minus D equals 4, you will get the value of D as 0.75. So you cannot increase D over 0.75. This is the maximum limit for you. However, as a signal or any pulse coming from microcontroller, D all of time will be from 0 to 1. But here for boost converter, you should limit the value of D to 0.75 to avoid increasing the gain over 4 times. Okay, شباب. For buck boost converter, شباب, the relation is D over D minus 1, and the same is also for CAC or check converter. Okay, and it's used for these two circuits. It's used to step up or step down up to the value of D. If D is from 0 to 0.5, it will step down, and if D is from 0.5 to unity, it will step up. Okay, so this is the way of controlling the output voltage by means of switched mode regulators. What is the difference between switched mode regulators and DC converters or DC choppers? Sorry, you have here inductance, and all of time you will use also capacitance at the output here. So this means you have storage element now, L and C. Okay, this L and C regulate the output voltage to be constant all of time. So the output of these four circuits will not be square wave. It will be constant DC all of time because of the capacitor and filters you have here. Okay, so this is the difference between DC to DC or DC choppers and switched mode regulators.
Sorry, Doctor.
تفضل يا شباب.
What's the difference between buck boost converter and chuck converter?
Okay, good. يعني this is we have some stability issues for buck boost converter if we increase the duty cycle over certain range, even if the gain is less than 4. For that, we prefer the use of buck boost converter. The difference, you will find that we have here 2 inductances, 2 capacitance compared to that one. Here you have only 1 capacitance and 1 inductance. So here this circuit is much more smooth compared to that circuit. So we prefer using chuck converter a lot compared to buck boost one. So this is the difference between them. However, it's possible to use buck boost converter with some limitations in load. Okay.
Even in electrical vehicle application?
In electrical vehicle, most of time we use bidirectional, not one of these topologies, because as we said in electric vehicles, you need bidirectional power flow. You need to charge and discharge. For instance, if you are working on ramp, going downhill on ramp, you need to return the energy to the supply. Is it right?
Yes.
So you have to return the energy to the battery. If the circuit is not bidirectional power flow, it will not allow that. So we design the circuit of electric vehicle to be bidirectional. All of these topologies here are unidirectional. The bidirectional one that can be used like this topology, okay, here, this one, which has 2 switches with anti-parallel diodes. This one can be used because the current can be positive or negative, as you can see. But with the help of inductance and the capacitance, we can add it. And even the circuit here is made for battery charger. Okay, so this circuit here can be used for battery charger. Is it okay?
Yeah, clear. Thank you, Doctor.
Welcome. Regarding AC voltage controllers, شباب, we have also many topologies. It can be based on thyristors like that. We can control the voltage by means of controlling thyristor as well. It can be also diode along with thyristor, but this topology is not preferred because you will have average value for the output volt, and this is not recommended for AC loads. All of time, شباب, AC loads needs 0 average volt, like the voltage what we have in homes. Okay, the positive and negative half cycles should be equal all of time. So the average value should be 0. So we don't recommend this circuit in industry. Okay, we prefer to use this one. This is single phase, and this is for 3-phase circuit. Okay, شباب. But to be honest with you, most of drives today do not prefer this type of AC voltage controller because it has lots of problems in terms of power quality. And power factor will be very bad, and also it will inject lots of harmonics on the AC grid. So we prefer, instead of using base thyristor AC voltage controller, we prefer to use something called PWM AC voltage controller. And it has different circuit شباب, and it's based on IGBTs or MOSFETs instead of using thyristors. Okay. And these are the 2 well-known techniques used for control شباب. One is called phase control and one is called on-off control. This on-off control is used for high inertia or thermal loads because it needs very low frequency compared to the other control technique, which is on-off control technique. تمام؟ يعني I'm شباب just describing very fast the different converters because it's not the main topic what we need to discuss in detail today. But the topics what we need to discuss in detail, inshallah, is the voltage source converter 3-phase one. So we have voltage source converter شباب, which is DC to AC converter. We said that we have 3 different DC to AC converters: voltage source, current source, and impedance source. And we prefer the use of voltage source up till now. Current source is not preferred, and impedance source is still new technology or new topology, so it's not used yet in industry. So voltage source converter شباب, It's just power electronic converter that converts DC into AC, but it has to be supplied by fixed DC source. So the condition of applying voltage source converter is to have constant DC supply يا شباب. طبعا constant DC supply can be obtained from controlled rectifier or even uncontrolled rectifier. Okay. The most often used power electronic devices for VSIs, voltage source inverters, are IGBT and MOSFETs. These are the most well-known switches used in the voltage source inverter. The concept of voltage source inverter شباب, is to provide a sinusoidal effective value, but the shape itself will not be sinusoidal. How? The ideal voltage of VSI is a sinusoidal waveform. This is the ideal waveform needed. However, in our life, nothing is ideal. So the practical waveform will be square or called quasi-square waveform يا شباب. So it will be oscillate between positive and negative. It's not a sine wave. However, we need to take the effective value as sinusoidal. So it needs special control in order to obtain effective sinusoidal waveform from the quasi-square waveform. How we can do that? We have to reduce the harmonic contents. We will understand, inshallah, the meaning of having harmonic contents in the output waveform. The high quality voltage source inverter, the lowest harmonic contents. So if you have lower harmonic contents, this inverter will be a high quality inverter, and it will be also expensive. In terms of cost, if you have lower harmonic output, the cost will be high because the inverter itself will be made in a definite control technique, which is sometimes complex and also includes internal filters. So the cost of this type of VSIs will be expensive. We have many topologies for voltage source inverters, like single phase, like three phase. We also have different operating techniques like square wave and pulse width modulation technique. And we are going to take care about PWM techniques because it's mostly used now in our electrical drives. So first, this is here just to discuss the concept of converting DC to AC. If we have sine wave like, DC wave, DC source like that, if we turn Q1 on, this is called the mode number 1. In this case, the output volt here on VAO will be Vs over 2, and the positive will be here and negative will be here. So this now will connect the output volt to DC volt. Now, shabab, in mode number 2, if we connected Q2, in this case, this negative sign will be reached to this terminal A. And the output voltage in this case will be minus Vs over 2. So if we would like now to draw a waveform, you will find that this is our voltage, shabab. VAN equals V out, which is Vs over 2 in positive and minus Vs over 2 in negative. Now, shabab, because this is positive and negative, it's AC supply. However, it's not sinusoidal. We need to have sinusoidal instead of having square wave like that. Okay? How we can do that, we will discuss it inshallah in here. طبعا يا شباب, for the currents, we have I1 and I2, which are the currents for the two switches. طبعا current will be the same as load current during the turn on of the switch time. So this is now the switch I1 for Q1, and this is I2 for Q2. This is for resistive load, ya شباب. If we have inductive load has different criteria, because in inductance you will store energy and return this energy again to the supply. So for instance, in positive mode, ya شباب, let's discuss this positive mode where Q1 is on. Here you will find the current is positive. How it can be? Let's go to the circuit again. Here, when Q1 will be on and you have inductive here, and if we added inductance here, so during turning on of Q1, the coil here will be charged. But if you turn off Q1, what will happen?
It will discharge.
It has to be discharged, and the current was moving in this direction. So it will continue through the other supply and return from die 2. So the current, in order to have the same positive current, diode 2 will work. However, this will happen when VS2 in negative will be connected to the load. So for that, you will find here D2 is connected and the current is still positive in discharging. But this is at the interval where V out equals minus Vs over 2. And the opposite direction, Shabab, for current, it will be also the same here. Yani the current will be discharging in negative at the period of applying positive volt. So you will find like a phase shift now between the zero crossing of voltage and zero crossing of current. This is the shift, Shabab, between them. And this is yani, already the factor or the delay that will affect the power factor of the circuit. Okay, so this is a case now of inductive load and voltage source inverters. Type. This is for single phase. What will be the output voltage relation in order to get the RMS output voltage? Now we don't need average, we need RMS because we have AC source. So for RMS output, Shabab, we need, or the effective value will be RMS value. How we can obtain RMS value for any waveform? Just divide 1 over the period and integrate the effective value during the period, okay? All of this will be under square root of 2. So, as you could see here, the output voltage, Shabab, this is the output voltage. The output voltage equals Vs over 2 and minus Vs over 2 for the second period. Type regarding the area, are these two areas, Shabab, equal or not?
Yes.
Yes.
It should be equal because we said here this is T0 and this is T0 over 2. So these two rectangulars are equal in area. So in this case, we can say now we can make only integration from the period from 0 to T0 over 2 and multiply the area by 2. So the relation will be T over T0, T2 over T0, which is the overall period, Shabab, of the cycle, for the integration from 0 to T0 over 2. So this is now the period for one pulse. Integration for what? For the voltage square. Actually, the volt was Vs over 2, so the square of the value will be Vs square over 4. And integration regarding dt, and all will be under square root of 2. When you do that for this waveform, you will find that the output volt RMS equal Vs over 2. طبعا this value, Shabab, it's effective value, right? But it's not sinusoidal. In order to know what is the fundamental component we need, yani for instance, when we supply this type of load by this source, AC load by this source, we need sinusoidal. We don't need square wave. And we need sinusoidal with a certain frequency. In order to understand what is the contents of this waveform, we can make a Fourier analysis. You know Fourier series, just used to analyze the components of any waveform, how much sinusoidal waveforms are included. So when we make a Fourier analysis for this waveform, Shabab, you will find that V out equals summation from n equals 1, 3, 5 up to infinity to Vs over n by sine n omega t, which means, Shabab, if you substitute here in this relation at n equal 1, it will be 2 Vs over by sine omega t plus its series. So we can continue, 2 Vs over 3 by sine 3 omega t plus and so on, plus 2 Vs over n by sine n omega t. What's the meaning of omega t, ya Shabab?
The fundamental.
Omega t here is the fundamental angle, where omega equals 2 pi f. So 3 omega t means you have 3 times fundamental frequency. N omega t means n times fundamental frequency. So this means now, Shabab, we don't have only fundamental waveform that we need. Yani, for instance, if we have 50 hertz frequency load or 60 hertz frequency load, omega should be 2 pi multiplied by 60. This is omega. But now from this waveform we will have not 60 only, we will have 180 and multiples. صح ولا غلط؟
Yes.
طيب, are these waveforms from 3 omega t up till n omega t or infinity, are these waveforms needed? Actually, it's not needed. We need only the fundamental one. For that, we need to make control technique in order to keep the fundamental and reduce as possible the other component. Other component, شباب, we call it harmonics. We have something called harmonic spectrum. Harmonic spectrum now, sorry. Harmonic spectrum, شباب, is a relation between frequency and harmonic factor. Harmonic factor, we'll discuss it now. What's the meaning of harmonic factor? But for now, we can get the relation not to harmonic factor, just fundamental. Maximum value. Maximum value of the waveform. Here, what is the maximum value, شباب, in case of fundamental? It's 2Vs over pi. Is it right? So we can come here, and this will represent, شباب, let's say n omega t, not frequency, because n omega will be the same. Okay, so this is n omega t. So here, this is fundamental at n equals unity, so this is omega t. And the peak value will be here 2 Vs over pi. This is called fundamental. For the third order, شباب, what will be the value? 2 Vs over 3 pi. So here, this is 1, 2 equals 0. So at 3, we will say here 3 omega t, and the value here is 2 Vs over 3 pi. 4 equals 0, 5 will be 2 Vs over 5 pi, and so on. Up till infinity, شباب, you will have values, but the value will be decreased. Okay? So, now, in order to understand how we can remove or decrease the effect of these harmonics, we need to make some evaluators, شباب, something called evaluation factors. What are these evaluation factors? We have something called harmonic factor, which is the ratio between harmonic order and fundamental. Let me make an example for harmonic order number 5. We said that harmonic order number 5 has a value of 2 Vs over 5 pi. Is it right? And you know,
Yes.
for fundamental, the value was 2 Vs over pi. If you compare, you will find here the result is 1/5, like that. So fifth harmonic order equal 1 over 5. Seventh will be 1 over 7, and so on. So the value of harmonic factor, which can be represented similar to what we have made here, يا شباب. يعني instead of saying here we have maximum value, لا, we can say even this is not maximum, sorry يا شباب, this is RMS. ولا احنا ما قسمناش على جذر 2؟ لا, okay, so this is maximum or big value. تمام. So if we would like to represent HF now, first one will be 1 because this is fundamental. Second one will be 1/3, then 1/5, and so on. For that, شباب, most of spectrum you will find this is 1, or we can call it as 100%, and all others will be per unit of the fundamental value. Okay, so this is called the harmonic spectrum, and you will find it a lot in any analysis for waveforms. Type. Now, is the harmonic factor sufficient to say this waveform is good or not? Actually, it's not enough. We need not only for certain harmonic order, we need all of harmonic orders in the waveform. So we have another factor, شباب, called total harmonic distortion. Total harmonic distortion now will collect all of the connected or equipped harmonics within the waveform. So it's summation now, and instead of having only Vn over V1, it will be summation to Vn from n equals 2 to infinity. Actually, we will not start from n equal 2 because even harmonics will not be there. All of time, even harmonics is 0 here. Even harmonics will be 0 for all of time. So we can start n equal 3, 5, and so on. And this equation يا شباب, because we have to add or summate orders up till infinity, which is impossible. We can get another equivalent relation, but exact relation, in order to get all of orders up to infinity. This is based on RMS, because the RMS value will depend also on the orders up to infinity. So, yani there is a derivation for this relation, but it's accurate relation and can be used for THD value. Okay, so just by knowing the RMS value of the square waveform we have, and the fundamental value, we can get the overall THD value. Just a quick example. I don't need to go through examples شباب in details. I just would like to hint some important notes. Here we have resistive load, and we have 48 DC supply with the circuit we already discussed now. So the output voltage شباب will be Vs over 2. So this is now the value of V output, what we need. Vs over sorry, لا دي حاجة تانية, sorry معلش. RMS output voltage at the fundamental frequency. لا ده الفundamental. لا الاوتبوت voltage شباب RMS output voltage will be Vs over 2, which is 48 over 2, it's 24. طيب. Now, if I would like to get the total harmonic distortion, I need to obtain also the value of V1. So V1 can be obtained as 2Vs over pi. If you substitute that, it will be 21.6. So you have now V1 equals 21.6, and you have VRMS equals 24. Use the relation of THD value, شباب, you will find that THD is 48.34. This is the value of THD. Now, what will be the value for THD for current? شباب. Actually, here we have resistive load. So it's expected to have the same shape of voltage waveform, because this is resistive load شباب. So the total harmonic distortion for current as well will be the same value, 48.3. Now, in terms of standard شباب, in low voltage applications, the maximum possible THD for current is 5%. So this means if you have this type of converter and you would like to inject the power of this converter to grid, it's impossible to be used. Why? Because it's below the standard limits. So in order to reduce the harmonic contents شباب, we have to find another way instead of the square wave operation. Okay? The same what we have discussed شباب for previous circuit can be obtained also, or can be made for full bridge. This is called the full bridge شباب. The previous one was half bridge. Okay? Full bridge will give you more voltage magnitude. This is the only difference. However, the concept is the same يا شباب. ماشي؟ طيب. It has also the same harmonic contents in case of resistive load. How we can reduce the harmonic contents شباب? By using different control techniques. Like what? Like single pulse width modulation, multiple pulse width modulation, sinusoidal pulse width modulation, modified. So we have many techniques شباب. Phase shift. We are not going to discuss all of this. We will take care about sinusoidal. So what is the sinusoidal pulse width modulation? We'll skip this and go to the sinusoidal. Sinusoidal pulse width modulation. Sinusoidal شباب, we will have two different waveforms. One is called modulating waveform, which is the sinusoidal wave here. This is called the modulation waveform. And another is called carrier. In order to understand شباب, please take care about this very important note. Can you see this modulation waveform? This modulation waveform شباب is the required output of the inverter. So, if you need output frequency equals 60 Hz, so the frequency of this one should be 60 Hz. For the voltage magnitude, how you can control the output voltage magnitude of this converter? By means of controlling the peak value of sine wave. So we have two factors which are very important now. One factor is called the modulation index. This modulation index, شباب, is a ratio between amplitude of reference, which is the modulation waveform, and amplitude of carrier. So if you make this sine wave now, شباب, with a big value equals to a carrier, you can get the maximum possible volt. Okay? If you make modulation index 0, this means that AR equals 0, which means the big value of the sine wave is 0. So you can control now the voltage output by means of modulation index by controlling the big value of the modulation waveform. Right. How it works, شباب? We have here many sawtooth or carrier waveform. To understand this, شباب, if you would like to have high resolution output with low harmonics, you need to make sampling for this sine wave for many times. Now the carrier is nothing, يا شباب, but sampling for the waveform. So if you have high frequency carrier, this will make many samples for the sine wave, which will produce output supply or output sinusoidal equivalent sinusoidal wave with low harmonic contents. So now we have another important factor called MF, or frequency ratio. Frequency ratio is the ratio between carrier frequency and output frequency. Output frequency, for instance, which is 60 hertz here. Carrier frequency should be multiples of these 60 hertz. So what do you think, يا شباب? How many samples we can make per one cycle in order to get يعني high resolution sinusoidal output? Hey شباب, what do you think?
10 times more.
10 times. If it is 10 times, by the way, it will be very يعني distorted waveform. يعني this means that you make switching frequency 600 hertz. You know, in most of applications, شباب, of AC drives, we prefer to have switching frequency with a value not less than 20 kilohertz. Why exactly 20 kilohertz? Because if the frequency or switching frequency is less than 20K, you can recognize the noise of that frequency by your ear. However, our ear cannot recognize any frequency over 20K. For that, we prefer to use higher than 20K, but sometimes we may have some limitations because of losses of the converters, and we will discuss this later, inshallah. So, يعني switching frequency, شباب, should be as much as possible high value, because this will give you very good resolution of sinusoidal waveform. For that, شباب, we prefer to have high frequency ratio. يعني we can make this frequency ratio 100, 200 like that. It's possible to be only 20, 15 like that, but the resolution will be very low. We will have some examples here to see the effect of increasing the carrier frequency. Fine. Here, these are the relations, شباب, of the single phase voltage source inverter and the Fourier series. Okay, but we are not going to discuss it here or to consider it here because we need to focus on three-phase one. This is the three-phase one, شباب. This is what we need to operate any AC drive, three-phase AC drive. So the circuit here consists of 6. تفضل.
بس time.
الساعة كام دلوقتي؟ اوكي. طيب okay, so we can stop here يا شباب at that point, and إن شاء الله يعني we can start from that point إن شاء الله in the next class. طيب. Any question يا شباب؟
دكتور